2016 was a year full of surprises, but one thing that wasn't a surprise was come the first Saturday of December, students all over the US and Canada were taking the notoriously difficult Putnam Exam. And hey, since it's December now, let's participate in some of that Putnam spirit and take on our second Putnam problem, even though this is the first year in a while that there is no Putnam Exam in December. But that's not going to stop us from taking on problem 1 from the A exam of the 2016 Putnam competition. This problem asks us to find the smallest positive integer j, so that if we take the jth derivative of any polynomial with integer coefficients, it will be divisible by 2016 when evaluated at any integer. And don't be intimidated by the length of this episode. This problem's not too tricky, but we're going to take it nice and slow to motivate every step of our solution. And hey, my coffee's ready just in time.
Coffee Time Math with your host, Wrath of Math.
Christmas is a-comin' and the egg is in the nog. Please do a problem from the International Math Olympiad. And if you haven't got an IMO problem, then Putnam will do. And I've got a Putnam problem that I'd like to do with you. Alright, let's do it. What have we got going on today? Well, we've got this problem here that certainly succeeds in appearing a bit intimidating, but I assure you it's not too bad. Of course, to understand this problem and its solution, you've got to be familiar with differentiation and taking derivatives of polynomials, which is basically just applying the power rule. Let's quickly read the problem. We've got to find the smallest positive integer j such that for every polynomial p of x with integer coefficients, if we take the jth derivative of the polynomial and evaluate it at any integer k, that will be divisible by 2016. So we've got to find the smallest positive integer j satisfying this condition. Now, I'm not going to give you a big recap of differentiation and the power rule. I'm going to hope you already know that in order to follow along for this video, but I will point out something important about taking the derivative of polynomials by applying the power rule. Say we've got this polynomial, p of x equal to, let's say, 3x squared plus, I don't know, maybe 2x. Each time we take the derivative of a polynomial, the degree of each of the variable terms gets reduced by 1. So here, our highest degree is 2. This means if we take the derivative of this polynomial twice, this term will have gone to 0, and this term will be a constant. Because what are we going to have if we take the derivative of this twice? Well, let's just write it out quickly here. We might write the first derivative like this. P with a 1 in the superscript, this is the first derivative of the polynomial. I said I wasn't going to give you a recap of the power rule, but here I'm going to kind of do it quickly. We drop the exponent down as a factor. That would be 2 times 3, which is 6. We reduce the exponent by 1, so that goes from 2 to 1 in the exponent. Here we drop the exponent of 1 down as a factor. That's 2 times 1, which is 2. And then the exponent gets reduced by 1, so that's 1 minus 1, which is 0. X to the 0 is 1, so we could just not write it. Then if we take the second derivative of this bad boy, which is just taking the derivative of the first derivative, we just apply the power rule again. 1 gets dropped down as a factor. That's 6 times 1, which is 6. The exponent of the variable gets reduced by 1, so that's 1 minus 1, which is 0. X to the 0 is 1, so we don't have to write it. And then the derivative of a constant is just 0, because of course the derivative gives us the rate of change. The rate of change of a constant is 0, because it's just a constant. So if we take the derivative of this polynomial, which has degree 2, because that's its highest degree, if we take its derivative 2 times, we get down to a constant. Of course, if we take the derivative of any polynomial enough times, we can get to a constant term. And if we take the derivative of this once more, we of course will have 0, because the derivative of a constant is 0. And then if we continue to take more derivatives, it's just going to be 0 over and over again. The point being, if we have a polynomial, we can take its derivative sufficiently many times to get to 0 over and over and over again. Then, turning the focus to the specifics of our problem, we don't know what our smallest positive integer j is, but it's something, and certainly if a polynomial has degree less than j, its jth derivative is going to be 0, which is kind of trivially divisible by 2016. So for all of our polynomials whose degrees are less than j, their jth derivatives are constants, so whatever we plug into them, it doesn't change what they are, they're just 0, which will be divisible by 2016, because 2016 times 0 is equal to 0. So indeed, 0 is divisible by 2016. Now, before I go any further, I'll put hints on the screen now, so you can take a look at those, and if you want to try the problem out yourself, they may help you find a solution. The basic idea is that we're going to find a lower bound for our smallest positive integer j that we're interested in. Then we're going to show that lower bound actually works, and thus it is the smallest positive integer that satisfies this condition. Now, we know that any polynomial of degree less than j is going to have a jth derivative that's divisible by 2016, since their jth derivatives are 0. But 0 doesn't really tell us anything about our smallest positive integer j. So now we might want to consider the simplest polynomial whose jth derivative is non-zero, and maybe we can use that to learn something about our positive integer j and set us on the right track to solving this problem. You'd probably agree that the simplest polynomial whose jth derivative is non-zero is x to the power of j. And again, we don't know what j is, but we know it's something, some smallest positive integer fitting this condition, so consider the polynomial that is x to the power of j. What is the jth derivative of this polynomial going to be? Well, let's just take it step by step and look at the first couple derivatives to get an idea of the pattern that will emerge. Of course, if we take the first derivative, the exponent drops down as a factor, so we have j times our variable term, whose exponent gets reduced by 1. So it's jx to the j minus 1. That's our first derivative. Then, if we take the second derivative, which is just the derivative of the first derivative, we drop the exponent down as a factor, so now we have j times j minus 1, and then again our variable term gets its exponent reduced by 1, so now it's j minus 2. And this pattern will continue all the way down to the jth derivative of our polynomial. And what's that jth derivative gonna be? Well, remember, each time we take the derivative of a polynomial, we reduce the exponent by 1. So in the 0th derivative, the original polynomial, we just have j as our exponent. When we take the first derivative, we have j minus 1. Second derivative, j minus 2, and so on, all the way down to the jth derivative, where we will have x to the power of j minus j, which is, of course, x to the power of 0, which is 1. Then, what are we going to have for the coefficient? What are our factors going to be? Well, notice how this was going. j times j minus 1, the next derivative would have been j times j minus 1 times j minus 2, so it's this sequence of factors, j minus 1, j minus 2, and so on, and notice in each derivative, the last factor is 1 greater than the exponent of the variable. The last factor here is j, which is 1 greater than j minus 1. The last factor here is j minus 1, which is 1 greater than the exponent of j minus 2. So the point is, the factors that we're going to have here making up our coefficient is j times j minus 1 times j minus 2, and so on, all the way down to the last factor, which will be 1 greater than the exponent That's 1 greater than 0. That's 1. And what is this, my friends? Well, that is j factorial. J factorial. And then, of course, like we said, x to the power of 0 is 1. So, in fact, the jth derivative of x to the power of j is just j factorial, a constant term. And why is this useful? Well, remember, j, whatever it is, it's the smallest positive integer that satisfies this condition. So the jth derivative of this polynomial that had integer coefficients, its only integer coefficient was 1, its jth derivative must be divisible by 2016. 2016 must divide this jth derivative evaluated at any integer k. Now, of course, whatever integer you plug into this jth derivative, it's not going to change what it's equal to because it happens to be constant. It's just equal to j factorial, which means, in fact, that j factorial must be divisible by 2016. So we could write that over here. 2016 must divide j factorial. Now, of course, this isn't an equation that we can solve for j, but we can use it to gain some useful information about j, since we know that its factorial is divisible by 2016. So what can we conclude about j if j factorial is divisible by 2016? Well, j is a positive integer. So what's the first positive integer whose factorial is divisible by 2016? 1 factorial is 1, that's not divisible by 2016. 2 factorial is 2, that doesn't work. 3 factorial is 6, that doesn't work. 4 factorial is 24, that doesn't work either. 5 factorial is 120, that doesn't work. 6 factorial, I think that's 720, that doesn't work either. Then maybe we start to write these out so that we don't screw it up. So what is 7 factorial equal to? Is that divisible by 2016? Well, by definition, it's equal to 7 times 6 times 4 times 3 times 2 times 1. We don't have to bother writing the 1. And then just breaking this down so it's a little bit more manageable. 7 times 6 is 42, times 5 is 210, so that's 210. And then 4 times 3 is 12, times 2 is 24. So 7 factorial is 210 times 24. To make that more manageable to do without a calculator, we can use the distributive property to calculate this as 210 times 20, which is 4,200, 4,200, plus 210 times 4, which is 840. And then this, of course, is equal to 5,040. 5,040. So 7 factorial is 5,040. Is that divisible by 2016? Unfortunately not. 2 times 2016 is 4,032, so that doesn't work. And 3 times 2016 is over 6,000, and that's too big. So clearly 5,040, which is 7 factorial, is not divisible by 2016. Now, this sort of guessing and checking might seem like a bit of a fruitless task and a silly waste of time. However, we know factorials get very big very quickly, so we're optimistically hoping that we won't have to spend too long looking for a factorial that's divisible by 2016. Let's check 8 factorial. Hopefully that works. 8 factorial, of course, by definition, is equal to 8 times 7 factorial. We already know that 7 factorial is 5,040, so what does that make 8 factorial? Well, it would be 8 times 5,040, which is 40,320. 40,320. Oh, look, that's very nicely divisible by 2016, because 2016 times 20 happens to be exactly equal to 40,320. So 8 is the first positive integer whose factorial is divisible by 2016. Thus, since we know that j factorial has to be divisible by 2016, this tells us that j has to be at least 8. J is greater than or equal to 8, which we can write up here as an implication. We don't know what our smallest positive integer j is yet, but whatever it is, we know that it has to be at least 8. Notice as well that since 8 factorial is an integer multiple of 2016, every factorial after 8 factorial will also be an integer multiple of 2016 because all the other factorials are also integer multiples of 8 factorial. And one more time, we know that j has to be at least 8 because if j were less than 8, it couldn't possibly fit this condition because this polynomial's jth derivative wouldn't be divisible by 2016 if j were less than 8. So j has to be at least 8. Then, since we know that we're trying to find the smallest positive integer j that satisfies this condition, and we know that 8 is a lower bound for j, we might be optimistic and hope that in fact 8 actually works and is that smallest positive integer we're looking for. So the next thing we would try to finish solving the problem is to show that 8 works, that the 8th derivative of any polynomial with integer coefficients will be divisible by 2016 when evaluated at any integer k. So how the heck are we going to do that? Well, I guess we'll use the blue marker. To start this off, we need a nice way of representing any arbitrary polynomial with integer coefficients. Thankfully, there's some very nice, elegant mathematical notation to help us out in just this situation. Remember that a polynomial is just a sum of a bunch of different terms, so we can represent our arbitrary polynomial, p of x, using summation notation. Say the mth term of our polynomial has a coefficient we'll call am, and then of course it also has a variable part, x to the power of m. Adding those up from m equals 0 to n, the degree of the polynomial. We know that each coefficient am is an integer because those are the types of polynomials we're interested in for this problem, polynomials with integer coefficients. Of course, it's possible that some of these numbers between 0 and n, the polynomial might not actually have a term of that degree. Maybe the polynomial doesn't have a term of degree 2. In that case, the coefficient a2 would be equal to 0. So this works just fine. Another important detail we might note is that we can assume the degree of our polynomial n is at least 8, just like j. And why can we assume that the degree of the polynomial is at least 8? Well, remember, if the degree of a polynomial is less than 8, then its 8th derivative will be equal to 0, and thus it will definitely be divisible by 2016. We're trying to prove that the 8th derivative of this polynomial, this arbitrary polynomial, is divisible by 2016. So if its degree is less than 8, we're already done. Its 8th derivative is equal to 0, so it's divisible by 2016. So all we have left to consider are polynomials whose degrees are at least 8. And remember, we're trying to show that for an arbitrary polynomial like this, its 8th derivative must be divisible by 2016, and so 8 is in fact the smallest positive integer satisfying this condition. So the next step, you probably know what it is, might seem a little intimidating, but we have to take the 8th derivative of this arbitrary polynomial. Thankfully, since we've got such powerful notation at our disposal, taking the 8th derivative of this polynomial is not that bad at all. We just have to remember the power rule. So what will we get when we take the 8th derivative of this bad boy? Well, each term will have its original coefficient still of am, but that coefficient will also have some other factors. When we take the first derivative, we'll get a factor of m. When we take the second derivative, we'll get a factor of m minus 1, and so on, all the way to the 8th derivative, which gives us a factor of m minus 7. Then what about our variable? Well, each time we take a derivative, the exponent reduces by 1, so the exponent in the 8th derivative will be m minus 8. Now, in the original sum, we went from m equals 0 to n. What are we going to start at now? We don't have to start at m equals 0 anymore, because notice, if m is equal to 0, 1, 2, 3, 4, 5, 6, or 7, then we're going to have a factor of 0 here, and so the whole term will be 0. So m doesn't need to be 0, 1, 2, 3, 4, 5, 6, or 7. M can actually start at 8. So this is a sum from m equals 8 to n. And hey, that's not so bad either. That is the 8th derivative of our arbitrary polynomial that has degree at least 8. Now all that remains is to show that this has to be divisible by 2016. Okay, then to show that this is divisible by 2016, you might think, wouldn't it be nice if we could just factor out 2016 from every term, and then of course every term would have a value that is its current value divided by 2016, since we factored out a 2016, and then hey, now we've written it as a multiple of 2016, so it's divisible by 2016. Well, we'd love to do something kind of like that. The problem with doing exactly that is that we have no way of knowing that all of this stuff divided by 2016 is an integer. Thus, we don't actually know if this would be an integer multiple of 2016. So what we have to do is rewrite this expression in some way that's going to introduce some division by 2016, or a multiple of 2016, but also in a way so that we know we still have an integer, even after introducing some division. So how the heck are we going to do that? Well, we might start to look at each part of this representation of a term separately. Look at am. What do we know about am? Well, not much really. It's just some integer coefficient. We don't really know anything about am. What about x to the power of m minus 8? Well, we don't really know anything about that either. This has to work no matter what integer we plug in for x, so we really don't know anything about that. So all that remains is this sort of string of factors, m times m minus 1 times m minus 2, all the way down to m minus 7. Maybe we can do something with that. When you see m times m minus 1 and so on down to m minus 7, and think about trying to replace this expression with something that involves some division, you might immediately remember how to write this expression as 1 factorial divided by another. We can write it as m factorial divided by m minus 8 factorial. That's what this is, right? It's m factorial, m times m minus 1 down to m minus 7, but then with m minus 8 factorial divided out. That gets rid of all the other terms, m minus 8, m minus 9, down to 1, leaving us with this, which is what we actually have. So we could replace this with this, and that would introduce some division while guaranteeing we still have an integer, since this is equal to an integer. But that still doesn't quite get us where we need to go, because we're still not dividing by any multiple of 2016. So we still want to divide this by some multiple of 2016. But again, we need to be guaranteed that it's still going to be an integer. So if you look at this expression and think, what could we divide it by to guarantee we still have an integer, what would come to mind? Well, if you're familiar with combinations or binomial coefficients, the thing that comes to mind would be this. Consider m factorial divided by m minus 8 factorial times 8 factorial. So we're including a new factor of 8 factorial in the denominator, which means we're dividing this by 8 factorial. What is this? This is, by definition, a binomial coefficient, m choose 8. m choose 8. I was writing it backwards there for a second. That is the number of ways that we can choose 8 objects without order from a collection of m objects, which is of course an integer. Now what's so great about this? What's so great about it is that 8 factorial, we already know, is a multiple of 2016. 8 factorial is equal to 20 times 2016. So now we have introduced division by a multiple of 2016 while still guaranteeing we have an integer. But of course, this here, this binomial coefficient m choose 8, isn't quite equal to what we actually have. It's equal to what we actually have divided by 8 factorial. So then we just have to multiply by 8 factorial as well to make sure we're not changing the value of our expression. And finally, we're closing in on the finishing strokes. If I lost you in the last minute or two, hopefully this will get you back up to speed with what we're doing here. Now we are writing our 8th polynomial, again, as this sum from m equals 8 to n with our coefficient am, but now we're replacing m times m minus 1 down to m minus 7. We're replacing that with this binomial coefficient m choose 8. m choose 8. However, remember, this binomial coefficient is not equal to m times all that stuff. We divide by 8 factorial in order to get the binomial coefficient. So to keep the value the same, we have to then multiply by 8 factorial as well. And then, of course, we still have our variable term, x to the power of m minus 8. Then finally, remember the big deal about this 8 factorial is that it is a multiple of 2016. So let's just pull that factor of 2016 out of the 8 factorial. And then finally, we can write this 8th derivative of our polynomial like this. 2016 times the sum from m equals 8 to n of am times a binomial coefficient, m choose 8, multiplied by what's left of the 8 factorial after we pull out a factor of 2016. Well, 2016 times 20 is 8 factorial. So what's left is a factor of 20, and then our variable term, x to the power of m minus 8. And isn't that dandy? So finally, what we see is that if a polynomial with integer coefficients has degree less than 8, then its 8th derivative will be divisible by 2016. On the other hand, for any arbitrary polynomial with integer coefficients whose degree is at least 8, in its 8th derivative, if you plug any integer into that 8th derivative, you'll just have that integer raised to a non-negative integer power, because m starts at 8 and goes to n. So you'll have an integer to a non-negative integer power, which is an integer, times 20, which is an integer, times a binomial coefficient, which is an integer, times am, which is an integer. So in total, you've got an integer, and then you're adding up a bunch of integers, and then you're multiplying it by 2016. That, my friends, is an integer multiple of 2016, which by definition is divisible by 2016. So we know that the smallest positive integer j, such that the jth derivative of any polynomial with integer coefficients will be divisible by 2016 when evaluated at any integer k, we know that smallest positive integer j has to be at least 8. And then we just showed that 8 in fact works. And so 8 is the smallest positive integer that fits this condition. And that's it.
The end.
Subscribe for more of the swankiest math videos on the internet.